And white. I don't know what that's about.
I also don't know what that's about.
I think my hair ranges a lot of colors.
So, first things first, I'm the realist. But beyond that, it's Friday, and it's been a minute since I've done it. But it's time for children's book time on Friday. I'm going to give you a choice. Your options are.
Definitely the P is for pterodactyl.
Your options are P is for Pterodactyl, the worst alphabet book ever, or the Star Wars ABC 3PO Galactic Basic Edition.
The worst alphabet.
Okay.
Alphabet book.
Alphabet book it is. Fair enough. All right. P is for Pterodactyl. Hold on, I gotta make sure and get this in the camera frame. All right. The worst alphabet book ever by Raj Halder and Chris Carpenter, and pictures by Maria Tina Badia. That's really your name? Feels like a stage name, but for like a writer. All right. A is for Isle. The bread aisle has not been cleaned in eons, and 90 tiny beasts meet to have a feast. B is for Delium. We doubt anybody knows what Delium is, but it's the only word dumb enough to begin with the silent B. I'm gonna make sure it's very clear on camera here, because obviously when they watch the video later about the class, this is why they're here, obviously. All right, C is for Czar. Shh, the fascinating Czar is secretly part Czech. Okay, D is for Djibouti. The boat race begins when the handsome judge from Djibouti drops his handkerchief from the bridge. E is for you. Eileen the ewe was so euphoric, the wolves were eaten. She even gave the eulogy. F is not for photo, phlegm, phooey, or phone. F is only for photo when you speak fluent Spanish at home. G is for Noki. The gnome yells, waiter, there's a bright white gnat nibbling on my Noki. Many words Spainhour had to look up in order to know how to pronounce correctly. That was one of them. I wanted to think that that was ganache. It's not ganache, it's Noki. All right. H is for air. The honest air admits that herbalism isn't his cup of tea. I is not for eye. We asked the pirate if he has two eyes, and he said, aye, aye. J is for highlight. Juanita and Bjorn happily played highlight before eating fajitas in Juarez. My grandma's name is Juanita. K is for knight. The noble knight's knife nicked the knave's knee. Oh, that wasn't part of it. My grandma's name being Juanita. That's not part of the book. It's just a little tidbit about me. Thought you should know. I'm failing right now.
Like there's a camera up there.
What's that?
You're looking up.
I am?
It's like an ominous person.
Yeah, you're like looking up there.
Oh, a lot of times when I like looking at the class, I don't look at you individually, and I can't. There's limited by human consciousness. There's 10 of you, so I look at you as a blob. And sometimes when I want to think, I look at the blob over there. It's fine. The center of mass is like here-ish, right? So I can look over there, and roughly we're in the right spot. Anyway, L is not for L. An elephant named L rode the L train halfway to El Paso and dined on the hearts of palm with her folks. M is for mnemonic, but Mr. M can't remember why. N is not for naught. N is for naughty children who will sing solemn hymns when autumn comes to an end. O is for Ouija. The French leopard says, we'd love to play Ouija with the wee witch from Oaxaca. That took practice. I'm not going to lie. I knew I was going to be reading this book, at least to physics 2. And so Luke and I practiced quite a few times on this book. Anyway, so if I screw up, yeah.
How scary would it be if his first word was Ouija?
That'd be cool. That'd be fine. All right, it's cool. All right, P is for pterodactyl. Ooh, this must be the climax of the book. All right, they said the title. Ptolemy, the psychic pterodactyl, struggles with psoriasis. That's a weird climax of the book. All right, Q is for quinoa. We can enjoy quinoa and quiche while by the quays of Qatar.
Wait, so is this like an actual story? Is it all these related? Oh, why is it?
R is not for R. In England, the Queen proclaims, we aren't going to say R's in butterfly, shark, or lizard. S is for seas. CC swam through the debris in the sea to see the imaginary Isle of New Arkansas. T is for tsunami. The charging tsunami washed away all of Tchaikovsky's tchotchkes. That one took a lot of practice. U is not for you. You would have never guessed that the wolf was disguised as the U.
That one wasn't.
It was part of it. It's true. Ooh, yeah, who knows what happened? V is for 5. How romantic. W is for wren. The wren wrapped the rabbit's gift in red, but forgot to write a note. X is for xylophone. Oh, good morning. Come on.
Spainhour, no kid would understand this story at all.
Not in your story.
Disagree. I have some, I have a couple nieces and nephews from Michigan. Holy crap, these kids are stupid smart, and they understood it all.
You don't understand that
Like,
it's
I
a joke.
get it, but
It's a
like-
joke because all the words, all the words don't. They're.
It's
We went up there. Actually, that's why I missed Friday, 2 Fridays ago.
Because
good morning.
he was so surprised by the song.
Thank you so much. Thank you.
What is like the group word for nieces and nephews?
Oh.
Like you say-
Nicefoos. Anyway, yeah, we went up there, and as we were driving up, it's not actually our nieces and nephews. It's weird. They're cousins of Jamie, but it's not important. Anyway, we were driving up there, and her cousin called her and said, like, "Hey, just as a heads up, have Andrew practice his chess because the 5-year-old wants to play." And dude freaking owned me. Okay, like, and I'm not amazing at chess by any stretch of the imagination. I'm also not exactly a dummy. And it was stupid impressive. Yeah, I think, yeah, it's not important. Okay, X is for xylophone. Xavier's extra arm, all right, made him an exceptional xylophone player. Y is not for Y. But Yevs, who was wearing yellow shorts, yells, "Why is the Eiffel Tower upside down?" And finally, Z is for Zhivago. Good night, Zhivago the zebra. I've enjoyed our rendezvous. Z's. There's the book. How do we feel? Well, thank you. All right. Here's the plan for today. All right, I'm going to let you kind of choose your own adventure, as it were. My plan up here is to go over the quiz as well as go over the horsey problem from the other day to try to give you a better understanding and take a little bit of space here. These last 2 days were kind of improvised because I can see that some people are kind of struggling a little bit. So you'll notice that right now there is officially no homework, which is kind of a weird thing for me to have for you, and that is done on purpose. So you have this next weekend. If anybody is kind of behind and needs to get a little bit more caught up, great. Or I know there's a handful of you that are still struggling on that lab. This gives you a little bit of space potentially to work on that right there as well, so that you don't. So hopefully it's not giving you more to get you behind. And then on Monday we will hit new stuff as well. So here's the plan. Either one. Okay, I want you to kind of go to the back of the lab table, and I want you to work with someone. You don't get to work by yourself, but period. And on either. No matter where you're at, 10 and 4. If you're done with 10 and 4 and you're like, oh, this is super easy, then do 3 and 6 and see how you do on those. Or if you don't want to do those, or if you are kind of a little bit more struggling, I am going to go over this entire quiz up front up here. And then after that, I am actually, like I said, I already said that, and I'm going to go over the horsey problem. So here's the quiz back for you first. Elena. Oh, real quick, also. Scores on here were given to you as like, this is what you missed. However, on Skyward, it's 6 out of 6. You did it. So no freaking out on me. All right. Ryan. Christian.
Tanner, what's your opinion on leaving the paper fragment on the side of the page?
I don't have a care in the world. My wife hates it when she sees it. Like Kennedy, she goes, "You let them leave those on there?" She goes, "I would take off so many points every time it happens." And then like, if I'm like nice and say, Alyssa, Anna, Quillen, if like somebody's missing a name, she goes, I wouldn't even let them turn it in. Like if you're a junior now, and she's partially right, like you're a junior now in a physics class. If you forget your name, that's it. That's just it. All right, Aaron and Xavier.
Well, it's like whenever like it's like whenever the genius like sucks at being on time, you know.
Sure. I got you.
But we're not doing it.
My wife currently works as a digital executive assistant. She works for like 3 or 4 different companies, but one of the main ones that she works for, she does scheduling and a lot of other things. So and it is her job to be like very like if I need something proofread, she enjoys that particular process of being very meticulous in the details.
You
So-
made it sound like she was a teacher and I was confused.
Oh, no. Just when she sees me like grading stuff and sees like people turn stuff in, that's what she usually gets here. All right, let's talk about it. Let's go up here. So I would like, if you are not gonna pay attention up here, and maybe everyone is, that's great. Go ahead, like I said, go to the back. And then if you want to pay attention to the lab, and if you want to skip out like halfway through, if you like get your questions answered or whatever, that's cool as well. All right, so the purpose of going over this lab is obviously it's not going to change any points whatsoever. The purpose of going over this lab is specifically so that you know, who am I addressing, by the way? Who's going to do the quiz? Okay, quiz, no quiz, no quiz, no quiz. You guys are all back there, that's great. So that's fine. Let's actually have you guys then, or you guys are going back? Let's have you guys kind of transition over here. By the way, tchotchkes, I found out because I looked up in the glossary, is a Yiddish word meaning tiny souvenirs. All right. Number 1. The problem asks you for the torque given by the ladder. Now, what is the only force exerted by the ladder? Gravity. And where is gravity going to be applied? In the center. Correct. Absolutely at the center. Now, one thing that people overcomplicate in this particular case is they see that this is at an angle, so they try to go, oh, what's the center this way? Or, no. It's just literally, if that's 6.1 meters, right, then this guy right here is just going to be halfway up. This is the distance, and I'll talk about why in just a second, or 6.1 meters divided by 2, 3.05 meters is going to be your lever arm. Now, the reason that's your lever arm is because the problem says calculate this torque about the bottom of the ladder. When it says about the bottom of the ladder, what is that telling you?
Like, that's the fulcrum.
Correct. It tells you that's the fulcrum. And the reason I do that is specifically so that we all get the exact same answer. Because if you place the fulcrum somewhere else, you're not wrong. You're certainly not wrong. You can place the fulcrum right there. Be Spainhour it's 0. You'd be right. You'd be 100% right. But we do this so that we all get the same answer. Now, the lever arm, by definition, is from the fulcrum to the force. So you can see right here, half of the total distance. Okay, force of gravity should be pretty easy. It's just going to, of course, be, I think you were given mass, aren't you? So mg, or 19 kilograms times g, or 182 and change, right?
So.
Yeah, 186.
186.2. 0.2 newtons. Okay, now this is just asking for an individual torque. And one big thing that came up on this quiz that I noticed that people in first hour struggled with as well is, wait a minute, Spainhour, how do I know when to use this for torque and this for torque? And the answer is this guy right here. Okay, this is an individual torque. And this only works when you talk about all of the torques at the same time. Okay, so in this particular problem, it only asks you for an individual torque, which is why this guy right here is definitely your best bet. In fact, we already have lever arm and force of gravity. The last thing we need to address is the angle. And what angle is given to you in the problem? No, not the number. Where does it go in the picture? What angle is given to you in the problem? Do you guys have a problem? I would. There, I could pull it up here as well. It's going to go right in the middle of it. Okay. What angle is given to you?
The end between the ladder and the ground.
Correct. So be careful on your pictures to actually put that particular angle, because what angle do you need for the torque?
Angle between the lever on the
Right, and hopefully you can see that pretty regularly, the way we're gonna do this, if I give you the wrong angle, is the answer is simply gonna be the complementary, because we've got this nice 90-degree guy right here, so if that's 70, that guy has to be 20. And again, the angle that you want is the one between the force and the lever arm. That's why this is the wrong one. Had, for example, had the problem, and I think this will come up later on a problem in your homework, asked for what is the angle caused by the force of the wall. That actually would be 70, because this angle here and that angle there are completely identical. They're all alternate interior angles, right? So they would in fact be 70. It's just important that you draw the picture in order to find that out. So of course, then you punch in sine of 20 degrees and your answer gets spat out as 194 meter newtons. Questions, concerns about any of that? All right, let's make this a little bit more proactive instead of me just like saying, hey, I'm gonna go over everything and you tell me what you need. Okay, on number 2, what would you like me to do? I can do the whole problem. I can just talk about the force diagram. What would you like?
Can you do like the whole thing? Because I'm pretty sure I got my force, what you call it.
Okay,
And that caused everything.
well, let's draw the picture here. What forces go on this particular picture?
Gravity.
Gravity in the center. Now, when we say the center, first most important thing when you have to deal with these rocks not being on the end is that's not the center between the rocks. Gravity doesn't know to go in the center of the rocks. That's the center of the plane. Right. All right, what else?
Like that.
And then there's normal on the rocks or whatever.
Correct, which we should label them differently. So instead of force normal, what do you want to call
Force rock on the board. Or board on rock.
them? I mean, no, if you're gonna do that, I would say force normal. I'm just gonna say, since they're both normals and both rocks, I would say just call them like 1 or 2 or something like that. Or left and right or whatever, whichever. All right, what else are you missing? Person or Frank, yeah, we got the force Frank. Which way is that gonna go? Now. Now, biggest mistake that I notice made by people on this particular guy is they try to do this force as well. This force upward, which does exist sort of, but not on this, because what are we drawing the force diagram of? The board, the plank, exactly. Okay, what is this the force of? This is the force of Frank on plank or bridge or whatever. What is this the force of? Plank on Frank, right? Which is fine. Feels like we're doing Dr. Seuss now. I didn't even do just Dr. Seuss, but it doesn't go on this force diagram. That's the bridge. That's the plank. That would go on the force diagram separately over here of Frank. And that would look like this: force of gravity down, force of plank on Frank right there. But obviously we don't need that in this particular case. Make sense? All right. Next, we're supposed to find basically force 1 and force 2. Let's go ahead and kind of work our way and find all the other forces first. What is force of gravity? I believe it's straight up told to you. Do you need to do anything with that 50 newtons? No, absolutely not. It's newtons. You don't overcomplicate it, right? When do you multiply by G? Why do we multiply by G here? I get mass, right? And of course, force gravity is equal to mg. All right, what else is given to you?
The plane is 4 meters long.
I'm sorry, in terms of forces right now, but then we'll knock that out as well.
Yeah, his pounds.
What is that about Frank technically?
That's like the
That would be his what? Weight, that is also his weight. Yeah, if I say 165 pound person, I might as well be saying the force of gravity is 165 pounds. Same as this 50 newtons right here. But obviously we can't leave it as 165 because we need to be able to use the same units. Also, we want an SI. So this is technically gravity, but that's why I drew this picture over here. That's technically this guy right here. But what do you know about those two?
people.
Not equal and opposite, they're just equal. I mean, you're right, they are opposite, but that's not why. It's not third law. Usually you say equal and opposite because of third law. Why are these equal? Not because of third law, but because of, yeah, it's first law. It's not accelerating. If Frank was jumping up and down, would these be equal? No, if he was accelerating, they would not be equal anymore. Because that's why you don't say equal and opposite in that particular way, even though it's sort of right. Okay, but his force of gravity is equal to this. How is this guy compared to that one? That is the equal and opposite one, right? Because that is third law pair in this case. So even though we're given this, does it also tell us this guy right here? Yes. So we're going to say force of Frank is 165 pounds, and then multiply by 1 pound, 4.45 newtons. And get that the weight of Frank is 734 point something. Yeah. We'll just go 734. I think it's fine. Yeah. All right. So now as you look up there, we've got two forces. We got gravity and we got force friction. And we're trying to find force 1 and force 2. I had somebody ask me the other day, he goes, why do you always start with torque? How do you know to start with torque? I don't know to start with torque. I try whatever's simplest. But as I look at that, why is sum of forces not going to work right now? I mean, sum of forces basically says everything up must equal everything down, which I think is true. But why is sum of forces not going to help me find either force 1 or force 2? Two unknowns, right? Now, if you got two unknowns, you got to go somewhere else either to get one or get another equation with two unknowns. That's why I know sum of forces doesn't go first. Right? There are a bunch of problems in these chapters where sum of forces is easy to go first. As a matter of fact, the horsey problem later, that's one that actually sum of forces can and should go first. Eventually, this latter problem comes back around and you see it again. And that one actually, once again, I do suggest summing the forces first. But in this particular case, yeah, we've got two unknowns. So that means I should probably go to sum of torques. And if I'm summing torques, okay, what's the first thing I have to do? Assuming that the force diagram, extended force diagram stuff. Well, okay, what's the advantage of placing a fulcrum in torques? One of the unknowns, because am I eliminating the force? Am I eliminating the force? No, I'm eliminating what torque it causes, because why does it go to 0? How do you calculate torque?
Oh, there's no lever arm.
There it is. There's no lever arm. So by placing the fulcrum directly on the force, there's no lever arm, which means there's no torque caused by that object. So your choice, where do you want to put the fulcrum? F1 it is. So let's go over here and sum the torques now. How much torque is this causing? 0. There is no lever arm. So let's go here. What about this guy? Positive or negative? Negative. This is going clockwise. This guy? Negative. This is going clockwise. This guy's positive. This is going counterclockwise. So we have negative torque of gravity, negative torque of Frank, positive torque of 2 equals 0. Question so far?
What would make force 1 be, or like the force 1 would be negative? If it's going up like that.
Force 1 could be negative if I move the fulcrum elsewhere. So I'll do that real quickly just for the sake of example, but we're going to go right back. Okay, like this would be a dumb place to put it for reasons we've already established, but let's put the fulcrum like just right here, just make some guess. Okay, and let's just run through all of them again. On this one, I'm going to go right to left. Right, this would be caused what? Cause for negative. Positive is going counterclockwise. This one would be negative because from clockwise. Now be careful because a lot of times people askew up and down with the same sort of thing, but here that's not the case. This negative causes, this force down causes a negative torque. This force down causes a positive torque. And now to answer your question, now force 1 is causing negative torque, right? Or I could move it once again, I could move it over here, in which case, again, these two don't switch, so I'm not going to talk about them again. But now this guy's actually back to doing the same thing as Frank. Now he's going this way again, so that would be negative, and force 1 is causing a positive in that particular case. Okay, so back here. So I know my answer. I'm trying to find force 2, and it's buried in this. So I'm just going to do algebra to isolate it ahead of time, just adding those to the other side. And even though that's not what I was trying to do, this does kind of say something relatively profound, and that's this. Okay, whenever I say sum of forces equals 0, it's simple. It's everything up equals everything down, everything left equals everything right. That torque just literally says, hey, everything going clockwise better equal everything going counterclockwise. Does that make sense? Okay, now we're trying to find forces, so I'm going to break down torque individualistically. I said this is the equation, but I've also told you, and you're for free, to say that this is the equation. When can I use the second one? 90 degrees, and you'll note up here that every single one of them is in fact 90 degrees, right? So just going to go ahead and make things simple here. If you're struggling kind of with seeing this, one thing I would suggest you do is do this picture, and then probably underneath, just draw a single line that looks something like this. Okay, so you can try to kind of like isolate specifically, you know, what's maybe going where. If this is too challenging to see, but angles that I was talking about, that's 90, that's 90, that's 90. Right? They won't always be, but in this case, all of them are 90. So my equation for torque 2 is R2 times F2. And like I said, we're using that second one, so we're not going to worry about sign. This guy is RG, FG plus RF. Forces for
Because they have the same variables.
And you can see the algebra is real simple. I'll just divide by R2. The hardest part, I would say, of this particular guy is getting what the heck the lever arms in this particular case are.
You were just curious.
Yeah, no, that's right. All right, so let's start here. The lever arm of gravity. One thing that I find to be helpful here is going to my picture, if I've done it well, and just saying, all right, where is the lever arm? All of these lever arms are technically different because I put the fulcrum here. Definition of lever arm is from the fulcrum to the force. Well, the forces are at different spots, so they all have different lever arms. Does that make sense? So I'm just going to put it right here and go, hey, this is the lever arm that I want, right? So the easy place to start here is to say, all right, force of gravity, where does it go? In the center. That's the center of the plank, not the center of the rocks. So I know that the total thing is 4 meters. Divide that in half to get 2 meters. What distance have I just figured out?
Distance from gravity to the end.
Correct. Gravity to the end is 2 meters. Now, if I want this, what easy thing can I do? Subtract 0.8, so RG should be 1.2. 1.2 meters. We've already established the force of gravity over there is 50 newtons plus, let's talk RF. All right, so that's from here to here. Not as easy to use that halfway point I was just talking about. So let's just start from the total. Okay, and try to whittle it down. The total's 4. What could I do to whittle it down? What's that minus the what?
0.8.
Minus the 0.8 would get me here. So I know this is now 3.2. And
Minus 0.6.
actually, let's just go ahead and knock it all out at once. Minus 1. So now we get down to this is 2.2.
Yeah.
2.2 meters times that, 734 newtons. Divided by R2, which is this. Again, I'm going to start at the same spot. Total thing, what can I do to whittle it down? Minus 0.8 gets me back to that 3.2 to here. What do I need to do now? To get 2.6. And you plug that all in your calculator, you should end up with 644 newtons and probably some change.
We have 11.
Questions, concerns on that? All right, so that is, of course, force of 2. Oh, we still need to find force 1. You have 2 ways to solve this, and I specify this every time, and I know it's kind of annoying when I keep going over stuff because sometimes it is easier to do the first thing, even though it's definitely not here, and I want you to be able to recognize. The first thing you could do is move the fulcrum, some torques again. Now you can literally move it everywhere because you know what this guy is. However, what is definitely going to be simpler here? We're just talking about sum of torques. Sum of torques is not simpler here. But sum of forces. We didn't sum the forces the first time because too many unknowns. Now we have one of those unknowns because we just solved it. There's only one unknown. Remember, sum of forces just says everything up must equal everything down, right? So I'm actually gonna get rid of the thing here so that I can use this empty space. So all we're saying here is sum of forces equals 0. Force is up, force 1, minus down, plus force up equals 0. So algebraically, I'd add those to the other side, but all I'm essentially saying right here is everything up equals everything down. So if I take everything down and subtract this one that I know is up, this has to be what's left over, right? Which should be 50 newtons plus 734 newtons minus 644 newtons, which if I'm not mistaken ends up as about 140 newtons, or like 139 and change. Questions on any of that?
I understand a little bit better. I drew my diagram wrong.
And it's just like force diagrams that I told you about before. You know, if you can't do force diagrams, it makes all this practically impossible because you're guessing, you're shooting in the wind. You're like it doesn't make sense past that point because of course it doesn't make sense. You don't have a good picture, a mental picture of what's happening in your head. You're not going to be able to, solve the rest of it like logically if you're kind of dealing with something that's not true anymore. Does that make sense? All right, so I'm gonna erase this if you're cool, all right? And I'm gonna talk about number 3 real quick. Do you guys does anybody want me to do number 3? I don't have to.
Can I ask you a question before you do that?
Sure.
Does on the foot force, whenever it says the total weight is 700 newtons, does that mean that the whole system has 700 going?
So
down?
imagine an outer picture of the person.
Yeah.
Right? It would be like this. Now, I showed you the other day that it's just a single foot, right? Of a person. It's just one, like they've got another foot up here. It's just this toe.
Yeah.
So the force diagram on that person would be force of gravity and force normal. So 700 newtons means force of gravity is 700, but that also means the force normal on the toe right there is 700.
But like the foot's gravity is not 700.
Foot's gravity is included in the 700 that we've already done.
But it's not 700.
Right, no, you shouldn't be putting the foot's gravity on there.
Oh, you shouldn't?
No, there's only 3 forces that should go on there. The foot's gravity is included in the 700. You don't need to put it anywhere else.
With the
force diagram is basically done for you in the picture. You shouldn't be adding anything to that. What's that?
I don't like the way it looks.
I'm
Mess
sorry.
with my brain.
This is how your foot works.
I'm okay, but I mean, let's wait.
I'm sorry.
Foot's are feet are
Okay, feet are fair, but as you walk back to your table, I think that you should be thankful apparently that it's real.
I am, but the picture looks it's weird.
Fair enough. Does anybody want me to go over the horsey problem, or are you guys good?
Was the horsey
Yes.
problem though?
The horse leaning up against the wall problem, number 7 from 8.5 of yesterday.
I do.
If you want me to go, if you're gonna listen to me going over it, come up here just real quick while I go over it. If not, no big deal. But I don't want to be talking to like the back of the room.
Do I need my phone with?
I don't care. No, I'll bring it up here. All right. This away. Did you get a chance to see my amazing background?
No.
This is my
Oh, yeah, I
amazing-
did.
Oh,
That's weird to me. I was gonna comment on it, but I don't think. Because it's like, I is the bear, I assume that's bear, riding Abraham Lincoln. And not the other way around.
Yeah, that's the problem with realistic in that particular setup right there.
See, I
That's
don't
the
like it when
only
you do
issue
that, 'cause it's like,
whatsoever.
I'm accepting the fact that an animate person.
I know, I understand what's happening. I get it. It's okay. A buddy of mine, one of my best friends from college, I've known him now 20 years. Okay, we met, and our first conversation that we had was actually after watching the movie 300, and we were in a big group of people. Okay, you know the movie 300, yes, ish.
I haven't seen it, but I.
Okay, so the movie 300 is 300 individuals, Spartans, okay, holding the line against millions, like thousands upon thousands of Persians all coming in, and they perfectly hold the line, yada yada, so on and so forth. Okay, we're in Steak and Shake, and I hear my buddy across the way go, you know what my problem with that movie was? The wolf at the very beginning was unrealistic, and I'm just gonna say this, okay? In a series of ridiculous things about a movie, you don't get to jump the list. You don't get to jump down to the wolf if the whole thing is already ridiculous. It's like people saying that, you know what, I don't think that a photon pack would sound like that in a Ghostbusters movie. That's the one you want to pick about unrealistic.
Also, it's like if the bear was shooting lasers, well, it's like, why is an animal riding?
You have obviously recognized that is a ridiculous picture,
For sure.
meant to be ridiculous. Why pick something out of it at all to be
Yes.
like?
It's weird that arguably one of the best,
I
Arguably
apologize
one of
for
the
this
best
on the
presidents.
thing if you're watching this for the horse problem. If you're not in here for the horse problem, I would have skipped out a while ago.
What's up?
one of the best presidents is being ridden by a bear whenever he could be riding. That is also shooting lasers out of its eyes.
Again, I'm just gonna pull it back up here and just go, there's a lot ridiculous about this.
Please. Okay, what's ridiculous about it? Because it's like they're in a battlefield. Other than
It's
the,
a gentleman bear. It has a mustache, monocle, and a top.
I'll be honest, I can't see the mustache.
Okay, he is holding an American flag that appears to be tattered, but has all 50 states, which is not the
It
United
doesn't.
States.
There's a hole in that flue. Oh, I see what you're saying. It's not an accurate
I mean,
Confederate or Civil War era flag.
sure.
You know
I mean,
what?
I guess that's not
Go on.
super ridiculous, but that's one of the, he's got the dexterity to hold it. Abraham Lincoln is shooting lasers out of his eyes and crawling on all fours while the bear is riding him. Like, I think I would probably start, if I were you, with the fact that the bear is a gentleman riding anything at
Well,
all.
think about it.
There's a president.
If they were switched, like I'm talking, the lasers are still there, but Abraham
Lasers,
Lincoln,
Abraham Lincoln still has the lasers,
No.
or they're on the bear?
they're on the bear, and that Abraham Lincoln is the general or the gentleman. It's fine. It's like weird, and he's holding the flag because obviously he can.
It's
hold-
obviously supposed to be weird. You're just arguing that it could be less weird in a way that makes you more comfortable.
I think it'd be cooler if it was the bear shooting.
We're done with this, right? All right. So let's talk about the horsey problem. Okay, the horsey problem is, I love this problem because if you understand tort, which I don't think, I mean, it's not an easy thing to understand by any stretch of the imagination, but if you understand it, it's a stupid easy problem. Okay, so let's begin. And if things are confusing, one thing I always suggest to people to actually begin with is do a normal force diagram. Okay, eventually you'll have to do the extended. You know you have to do the extended, but do a normal force diagram with what you got. Well, the other thing that I think kind of does confuse people a little bit is this. This W is actually what? Gravity. Yeah, it's the weight. That's what it's like. A lot of times forces use W instead. A lot of textbooks use W instead. So we have force of gravity down, and apparently we have a force of wall to the right. So let's just do a force diagram to look at this. And by that I mean, all right, if there's a force down and the horse is not accelerating, which we don't expect them to be, then there should better be a force up. What's probably providing that force up? Normal, or specifically the ground, but yes, there's normal up. All right, and if there's a force of wall right, there better be a frictional force left. All right, now let's take this and go over here. And note that these two are already on the drawing. Now, you can, as they did right here, draw the force of wall here. You can also draw the force of wall like this. Both are kind of equally fine, although the second one is probably what you're a little bit more comfortable with, but they're the same thing. All right, next, where should the other forces go?
Friction on feet.
Friction's on feet, going which way?
Left.
Left. All right, and
No.
Also on the feet, correct. All right, now let's begin with a complicated problem with what is arguably the easiest method of analyzing it, and that is summing the forces. You can actually use sum of forces to do something pretty easy, pretty quick. I think that actually straight up answers part B. For starters, force of gravity equals mg, so it's 500 kilograms times g, which if I'm not mistaken is 4,900 newtons. Okay? What could you do with sum of forces to calculate one of the unknowns up there? Because technically we have 3 unknowns, right? Right, we have gravity, sure. What could you get with sum of forces? Normal, right. Technically, you could straight up sum the forces ahead of time and get, hey, force normal is up, force gravity is down, awesome. I have that force normal is equal to force gravity, so 4,900 newtons. Got it. And we could do that because we had one of the 2 of them. Why can't we sum the forces to get force wall in part A? We don't have either. We don't have either force, which means I probably need to torque. Sum the torques, correct. Which means I need to do what? Now, set a fulcrum. Okay. I tried to comment on this a few times by talking about my force diagram right here. And when I say understanding forces, it's this. You can calculate force in 2 ways. You can do this, or you can do this. Okay, I'm going to rearrange this real quick to show you what I mean. Okay, I'm just going to move this, switch these 2. Makes you feel a little weird, but that's okay. The purpose of getting the angle and the R is to get how much is perpendicular. So if I were to draw the lever arm for weight, for example, right here, I would draw the lever arm like this. I would draw from this to the fulcrum, and the angle would go right here. But our sine of the angle would give me what piece of that triangle?
Or that.
Which it already straight up tells you. Yeah. Meaning you want to use this equation, right? So when you sum the torques equals 0, there's only 2 things causing torque. Weight is going to cause it to spin like this, so positive or negative. Positive, I'm going to call it gravity instead of weight. Yeah. And then walls causing it to spin like this, so which makes sense because torque of gravity better equal torque of wall. And right here, with the gravity I was just talking about, this should be R of gravity perpendicular to force of gravity equals R of wall times force of wall. And this number is just going to be 0.35. In the exact same way, let me do this for the wall now. What's the lever arm for the wall? Where it would be here. Okay, right there. And the angle for the wall would be this guy. Or if it were here, or also this guy. Both will work just fine. But I wanted to use this guy specifically, this angle, because I wanted to show you this triangle again and ask you if this is R and this is theta, what is R sine theta? 1.2. Yeah, 1.2 because it's the height right there. So literally force of wall is just RG 0.35 meters times 4,900 newtons divided by 1.2 meters. Does that make sense? If that makes sense, the rest of this goes stupid easy because you already know the answer to B, right? And this asks for what's the minimum coefficient of friction and how do you get the coefficient of friction?
Force friction equals the equation for friction. The equation.
Force friction over force normal. So it's literally just, I mean, okay, technically we don't have force friction yet, but if you have force wall, I mean, do the math, sum of forces in the x equals 0, plus force wall minus force friction equals 0. So force wall equals force friction. So literally take your answer for A, divide by your answer of B, and you've got the answer for C. How do you feel about the problem now in the future?
Well, I feel like you've explained it to me.
Well, that's fair. I'll just say, you know, again, kind of things to clue you into knowing that this is what you should look at it as is when you've got forces that are straight up orthogonal, okay, meaning not diagonal, left, right, yeah, up, down. I say orthogonal and I forget that's not like a standard word, most people know. But you see them left, up, down, right, and the distances that are given to you are not the lever. I mean, shoot, you technically could overcomplicate this and you could find the lever arm. The lever arm would just be trig, that squared plus that squared square root. And then you could find this angle also with trig. But then once you did that, the r sine theta with that r, that sine theta is just going to spit out 0.35 that you already have.
That's why I got it wrong.
And then the other issue, of course, being is you can't do that here because it doesn't tell you what this particular distance is right there. Yeah, but again, even if you did, it would end up the same way. So, all right, calling the video right here. Hopefully that was helpful.